Okay, we're 2 minutes past. I think we can start. So thank you so much for joining this webinar. We have a very exciting topic and a very dense session ahead of us, right? So a couple of admin items. Yes, we're recording. We will share the recording with you in a follow-up email. It will also include slides and a bunch of other links, right? So we do not want this to be fire and forget session, right? And we're hosting many more enablements on the topic of building generative AI and agentic applications on AWS, right? So you will get everything, okay? So with admin stuff out of the door, let's take a look at a few interesting numbers. Now, according to Gartner, about a third of all enterprise applications will be powered by agentic AI within 3 years, right? Comparing to less than 1% today. And at least 15% of work decisions will be made autonomously by agentic AI within the same 3 years. Again, compared to about 0% today. But this is not just future, right? This is a transformation that is already kind of happening today with all of us. So we've been working with customers across virtually every industry in their generative AI and agentic strategies. And we're seeing agentic AI creating business values in several key areas. Things like workplace productivity, right? This is a large segment of agentic AI where your agents seamlessly integrate with tools like Zoom or Asana or your IDE, etc. Business workflows, not just productivity, it's also business, right? AI agents streamline operations across functions like financial reporting, demand forecasting, incident management, etc. And obviously innovation and research, right? Automating simulations, allowing researchers to focus on strategic ideation. Now, this is nice, but what is an AI agent, right? We've been using this term a lot lately as an industry. What is that thing, right? So at AWS, we define AI agents as autonomous software systems that leverage AI to reason, plan, and complete tasks on behalf of humans or assistants, like compiling research, paying bills, planning a trip, etc. But what does it actually mean? How do you build something like this? So this is going to be our primary topic for today. What is an agentic system or AI agent? How do you build one, right? What does it entail, right? And how do you actually run it in cloud? So in order to answer this big question, what are AI agents? We'll start with a quick journey into generative AI evolution. Now, as any experienced engineer knows, before building a system, you need to understand why you're building a system, right? This is exactly where we're going to start. So many of us have learned about GenAI just a few years back, right? When we first saw something like this, an interface to ask questions. And this can be Claude, Desktop, or ChatGPT, or any other similar AI assistant that you're familiar with. Now, under the hood, it was using large language models, right? It's a technology, right? This model was trained on a huge volume of data, and your assistant was essentially an interface for that LLM, like ChatGPT or Cloud Desktop, like I mentioned. You were asking questions. LLMs were generating responses based on the training data. This was super fun to experiment with, right? You could ask a model to write you a poem about serverless, for example, and voila, it was actually able to do so based on its training. It was fun to play around with, but the excitement with basic stuff was quickly augmented with realization of the limitations. Now, try asking your LLM a question about something real time. For example, something as simple as what time is it or what's the weather. The thing is, LLM doesn't know. This is not something that LLM was trained on, right? So it definitely has no idea what's happening right now. LLM by itself cannot tell you what time is it right now. It has a knowledge cutoff date of about 6 months ago, so it definitely doesn't know anything about the weather. Ask your LLM for sales data for your department. Well, it doesn't know, because it doesn't have access to that data. It was not included in its training. LLMs just doesn't know this personalized data. Ask it to book your trip to Paris, for example. Well, the thing is, LLM cannot do that. And it explicitly tells you about it, right? You're not able to make actual bookings or reservations directly. So to summarize, there are several interesting limitations to LLMs. So first of all, LLMs don't know what they don't know. Sometimes they might explicitly tell you so. Other times they might produce fluent but totally fictional answers, right? So LLMs, they don't know what they don't know. Second is LLMs are great when you need to generate results based on their training and some statistical patterns. On their own, they cannot perform actions or interact with the world. And the last one is LLMs are actually stateless. They do not retain memory between interactions. They do not remember who you are or what you were talking about. They are only aware of things you include in the current prompt. It's called context window. So to state it very explicitly, again, they do not remember you. They do not remember your previous conversations. And now you might be thinking, but that's not exactly my experience when I was using Claude or ChatGPT or Amazon Q, right? So dots are not connecting here, right? Bear with me. You'll see how it works, okay? So, we know these three limitations. Let's see, how can we actually address them, right? So let's run a simple experiment. Let's ask your favorite LLM, how much is 1 plus 2 plus 3? It will happily give you an answer, right? Now, let's make it a little bit more interesting. We're going to be adding additional context. For example, 1 is apple, 2 is peach, and so on. So LLM gladly consumed this context and was able to generate a much more suitable response, right? So let's pause for a second here. Does it mean that we can inject context into prompts to make LLMs smarter? And the answer is yes, we absolutely can, right? This is exactly how we're making LLMs smart. So let's take a look at a simple example, and we'll gradually build from basic stuff to more complex. So let's use this context injection technique to give our AI assistant, not Agentic yet, just AI assistant for now, a bit of a personality, right? Remember this diagram? This is where we started. So let's make one small change. Inside of this AI assistant, we'll define what's called a system prompt. Let's say you want your assistant to behave like a famous French chef, right? So what's going to happen now is every time your assistant sends a prompt to LLM, it will include both user prompt and system prompt. We'll call it a composite prompt. Basically a prompt that includes multiple components. Now let's see this in action. I'm going to ask my assistant a very generic question. How can you help me? Again, not suggesting anything. How can you help me? Now, and as you can see, the answer is heavily influenced by the system prompt we defined in the assistant, right? So as a user, I don't need to specify it in my user prompt on every interaction. My assistant application code will inject the system prompt to every call it makes to LLM. Let's see what else we can do with this technique. So we already have the system prompt defined, right? So let's define another property, and we're going to call it history. And this is going to be an array of messages representing your conversation with the LLM, both user prompts and LLM responses. Now, on each request, the assistant will supply LLM with user prompt, system prompt, and full conversation history for the context. This is how you're getting the feeling that LLM remembers you. In reality, it's your AI assistant that manages the conversation history, not the LLM. But can we use this technique to also inject business-related data into the prompt? And the answer is yes, we absolutely can. This is called RAG, or retrieval-augmented generation. And the idea of RAG is to have a pre-populated enterprise knowledge base, for example, thousands of legal documents that your company processes over the years. And usually this knowledge base is stored in a vector database in form of embeddings. I'm not going to go too deep into what embeddings are. Think of this as a format that is very easy to search semantically. You can easily find similar things. So whenever user sends a query, the AI assistant first queries that knowledge base and retrieves information semantically relevant to the query. Once retrieved, it adds it to the composite prompt and sends the whole thing to LLM, which generates the response, right? So we're gradually enriching prompt to LLM with additional context information. So with Reg, the prompt like get me sales data for my department for last week would yield a much better response. Now you can actually see the data you were looking for, right? With Reg, you can enrich LLM responses with factual historical data. Now, let's take this one step further. There's still one interesting limitation that we need to address. What if my queries are about something that LLM was not trained on, and also something that cannot be retrieved using Reg? For example, what are the concerts I can go to next weekend? How do you think it will handle a question that involves, first of all, knowing my location, right? And second, information about future events, something that was not part of LLM training or Reg, right? Surprisingly, my assistant handled it quite well, right? I got a very impressive response back. It recognized that I'm based in Austin, Texas. This is true, right? It recognized the dates for upcoming weekend and managed to get me a good list of upcoming concerts. And this is not hallucination. Those are the actual concerts. But how did it know that, right? Like I said, it's not part of the training for Reg, right? And the answer is hiding right here at the very bottom, right? So guess what's going to happen if I click that sources button? Now, obviously, LLM didn't know my location or magically predicted the concerts, right? However, my AI assistant is connected to various tools that can help to get this missing information. So my AI assistant actually browsed the internet, found all these websites, found concerts for Austin, parsed and aggregated all this information, fed it to LLM, and generated the result that I'm very happy with. And this is just a simple example of what's called an agentic AI workflow, a multi-step plan of actions that was autonomously generated and executed based on my prompt. Let's see how it works in more detail, right? So it all starts with AI assistant, and this time agentic assistant, or simply AI agent, sending a prompt to LLM. But this time also supplying a list and descriptions of various tools it has available. Literally saying, if you need me to search web, I can do it. Based on the tool description, LLM can ask the agent to use one of the tools to get more context required to addressing the problem, right? The prompt. This is exactly what happened in the previous example. The agent calls relevant tools, which might be connected to enterprise data sources, web browsers, whatever you want, right? And retrieves the required result. After that, the agent sends two results back to the LLM. And depending whether LLM needs additional context, it might ask the agent to perform this loop several more times. This is dynamic. This is not a pre-programmed workflow. Once LLM is satisfied, it will return the final response. This is an example of a simple agentic workflow. So to summarize this section, right, this is what we call agentic loop. This is what agentic systems are all about, right? Agent receives input and some context, calls LLM, picks a tool according to LLM response, executes it, updates context, and then the cycle repeats, right? In a nutshell, you can think of AI agents as applications that are calling LLMs in loops and then doing whatever LLM asks them to do. This is what agents are all about. So now that we know what agentic system or AI agent is, right, let's actually try to build one, right? So this is the core use case I want to address with you in the next 45 minutes or so, right? Together, we'll build a travel agent, we'll test it locally, we'll deploy it to AWS, we'll extend agent's functionality with internal and external tools for MCP, right? Also running on AWS. We'll explore operational aspects like security, observability, etc. Right? So we're going to be building this travel agent now. Without further ado, let's start by implementing the AI agent based on everything we know so far. We're going to be writing some code, right? Don't worry if you're not a Python expert. This is going to be a very conceptual pseudocode, right? It's going to be very easy to understand, right? Not going to be any complexity here. So we start by defining this AI agent function. First, we'll add things like system prompt, maybe some Reg context, a list of tools that we'll be using, right? And we'll build a composite prompt that includes all of these components, history as well, etc. Note that at this stage, this is not an agent just yet, right? It's just AI assistant preparing to query an LLM. It's not an agent just yet, okay? This is where things start to be agentic. We start our agentic loop. The first thing is we'll call to the LLM and update conversation history, both user prompt and LLM response, right? Next, we'll check whether LLM is asking the agent to use a tool, right? So if response status equals call tool, again, pseudocode, right, we'll invoke that tool, right? And we'll create a new composite prompt, this time including the response from that tool. So invoking a tool and then updating the composite prompt. So the agent can invoke LLM again, and this time with tools response, and call tools again if needed, and so on in cycles until LLM doesn't want the agent to use a tool anymore, right? This is where agent breaks the loop, right? This essentially means that LLM has supplied its final answer. And the last thing to do is to return the response back to the client, okay? Now, this looks simple and easy to implement, but there is one big problem with this code. This whole thing is just a boilerplate, right? Because, think of it. It doesn't really matter whether I'm building a travel agent or financial advisor agent or cooking agent. This boilerplate is exactly the same. I always need to maintain history. I'll always need to maintain state. I always need this agentic loop. I'll always need to dynamically call tools based on LLM responses. What differs are parameters. Things like system prompt is different, right? The tools that I use are going to be different, but you always need to update history, generate composite prompt, have that while loop, and so on. So to overcome problem, instead of writing this boilerplate, I highly recommend you would use battle-tested frameworks and services that abstract I call them agentic commodities, and allow you to focus on what's differentiating your agent, right? So today we'll use Strands Agents SDK. It's an AI agent SDK that was created by AWS for builders who value flexibility, speed, and simplicity, right? I don't show examples from Strands SDK, but essentially this information applies to any other agent building framework like LangChain and so on, right? So with Strands, it's pretty flexible. You can use any model, including models that run locally on your machine. You can deploy to any compute type. You can create your own safeguards and guardrails. Comes with native observability, integrated tools, and so on. I don't want to go through each bullet here because you will see a lot of that in the following slides. So let's see how you actually use Strands SDK to build a simple agent. So to start with, you define which LLM you want to use. Now, as I've mentioned, this is a Python framework, right? It's available in Python, right? You can specify that you want to use Bedrock or any other LLM provider. Again, like I said, fully customizable. Now, if you're okay with the default provided by Strands SDK, you don't even need to implement this, right? You only need to specify your model if you want to customize this configuration. Now, the next step is let's create an instance of an agent class, right? And specify the model that you want to use. Again, you only need to do this if you're specifying other than a default. And that's pretty much it. From this point on, you can start asking your agents questions or give it instructions. All the agentic loop implementation specifics are abstracted from you. Your agent maintains state, history, tools, and so on, right? So, this agent class abstracts all of it. So far, this is just a piece of Python code. It's not a cloud application just yet. It's Python code. If it's just Python code, let's just try running it, right? Keep in mind, remember the prompt. How can you help me? Well, this is what we're getting back from the agent and LLM, right? A very generic response, as you would expect, right? I can help you with wide range of tasks such as, and you can see the list. Well, why is that, right? Because we wanted to build a travel agent. Why are we getting this generic answer? Well, because we haven't defined the system prompt just yet, right? As we've discussed. So let's do it. I'm going to add a new system prompt property to my agent. And this is where agent's personality, so to say, and rules of engagements are defined. So here I'm explaining to the agent what its mission is, right? And you can see I only have like 3 lines of code here for demo purposes, but you can, in real agents, you can see those system prompts being several pages of text. with detailed explanation how this agent should behave and what are the workflows that it supports. Now, if I run this updated code again, I'm going to see a very different response, right? So with just a simple change of adding system prompt, I've completely changed how my agent behaves. Now it's fully aware of the fact that it's a travel agent, right? By defining system prompt, you can better shape the agent reasoning, constrain its actions, and align outputs with the intended text, right? As you can see on your screen. Okay, let's test another interesting claim I made previously. I'm going to run two prompts. The first one is, I always dreamt of visiting Tokyo. The second one is, what language do they speak there? Okay, why is this interesting? Well, because there in the second prompt clearly relates to previous prompt, right? Now, according to the claim I made earlier, the agent should be able to process this nicely, since it maintains internal conversation history and sends it to LLM in each prompt, right? Let's see if it actually works. And as you can see in the second response, I am getting the expected result, right? So this means that my agent is indeed maintaining internal state with full conversation history. But this becomes a bit more interesting when you start to think about deploying your agents to the cloud, right? Now, this is probably what your initial architectural diagram is going to look like. Agent running in cloud with state management. However, in reality, you do need to keep in mind that agents are essentially just applications, right? You saw that. I'm using Strands SDK framework to abstract the agentic loop, but outside of that, it's just a Python application. And when you're running applications in cloud, you might have multiple instances of your applications, right? It's very common for scalability and reliability purposes. So if you're going to store that state in each agent application instance separately, right, internally, your user experience is going to break. Each request might hit a different instance of your agent, which do not have full context from previous invocations, right? So how do you address that? Well, just like you do it in any other kind of cloud application, right? You want to keep your application stateless, and you externalize the state to some external storage. With this approach, each agent instance will always get the most up-to-date state, right? Which contains full conversation history. Let's see how to easily implement this with the Strands SDK. Now, your agent conversation history is stored within the agent.messages property. You can see it if you just print that property. It's literally an array of JSON objects representing previous conversations between agents and user, right? Including user queries and agent responses. If you're using tools, it will also include tool responses, etc., right? It's just a JSON array. Now, if it's a JSON array, I can very efficiently store it externally, right? First step is we're going to pick the storage that we want to use. I'll be using S3 here since it's fast, it's cheap, it's super scalable, and it's supported by Strands SDK out of the box, right? So what I need to happen is, first of all, prior to my agentic interaction, I want to restore previous session state from S3. Now, during the agentic interaction, I want to update the session state, right? This means new messages from user and assistant will be injected into the state, right? So the state needs to be updated with the next agentic interaction. And the last thing is, once that agentic interaction has completed, I want to persist session state back to the session storage. So next time I'm getting the up-to-date session state. And the big question is how I actually achieve this in the most efficient way. Well, like I said before, Strands SDK comes with built-in support for using S3 as session storage. Just use the S3 Session Manager class, specify the name of your bucket, and optionally whether you want to prefix your objects. This class will automatically take care of persisting and restoring sessions on each interaction, right? You don't need to manually read data or write data to your preferred storage. The class, right, the session manager will do it for you. So the only thing left to do is to actually configure your agent to use the session manager, right? And that's pretty much it. So by externalizing the state, you achieve, and this is important, I want to emphasize that, you achieve a fully stateless agent while at the same time providing a stateful experience. So from the experience perspective, users think the agent remembers them, but the application that implements that agent is actually fully stateless because you're externalizing that state, right? Now, I've mentioned S3 Session Manager. Session Manager is actually an interface. So if you want to store your sessions in some other storage, you can just implement that interface and any type of storage can be used, right? It's just this one is available out of the box and it's very efficient. But there's one more catch here, okay? This is what agentic interaction commonly looks like we mentioned on the architecture diagram. While you got a single user icon here, in reality, you might want to have an agent that knows how to distinguish users, right? This is especially relevant for travel agents we're building, right? Just like a regular application, you need to decide whether you want your agents to be single tenant, multi-tenant, user agnostic, user aware, right? Essentially, your agent needs to understand who is the person, right, or source they're talking to. So the next thing we'll do in our travel agents is we're going to add user authentication and authorization. I'm going to be using Cognito. You can use any existing enterprise identity provider of your choice. Okta, Auth0, Ping, ADFS, anything you want. The user will first authenticate with Cognito and obtain access token, right? When making requests to the agent, the user will pass that access token to the travel agent. And the travel agent will validate this token. I'm not talking about how yet, right? I'm just talking about the fact that I need authentication and authorization in my agent, right? So from this point on, my agent is identity aware, which means I can enhance it even further. For example, I can store session state associated with user unique ID, right? So essentially now my session state, it's not just one user agnostics JSON. Now I'm actually saving it separately per unique user ID, right? So each user will get a personalized experience. I'm going to introduce a minor change in my code that will take care of that, right? And this, you can see there at the bottom, on top, right? So now I'm using users identifier when creating a session manager instance. And this is the result that I'm getting. My agent knows my name. It can provide personalized experience and even propagate identity to downstream dependencies, as you will see soon, right? So far we've built a nice setup that kind of works locally, right? And it's time to deploy to AWS. So the big question is which compute service I'm going to use, right? Well, when you're using Strands agents SDK, your agent, like I mentioned several times, it's essentially just a Python application. So you can deploy it to any compute option you like. It can be Lambda, it can be CF or EKS, it can be the Bedrock Agent Core runtime that we've announced last week, right? It can be anything you want. It's just a Python application. I want to emphasize this again, right? Think of it as a microservice, right? The difference between, traditional microservice is, the traditional microservice, they interpret incoming requests syntactically. They look at the payload structure, schema, the JSON or XML or whatever you're using, and then they're parsing that and running a predefined workflow, right? That's how microservices, traditional microservices operate. Agents are also microservices, but they're different because they interpret incoming requests differently. They interpret them semantically using LLMs, not syntactically, but semantically. They're trying to understand it, again, using LLMs. And then they adjust the workflow dynamically based on LLM's response. That's the core difference between traditional non-agentic microservice and the microservice that actually implements agentic logic, right? Agentic logic will use LLM to interpret requests semantically and adjust the workflow dynamically. Now, as a serverless guy, I want to spend as little time as possible managing infrastructure and focus on delivering business value. So I do want to run my agents on more of a serverless compute options like Agent Core or Lambda, Fargate. But I also want to make sure that my agent is portable from the get-go. in case maybe in future I need to run it on a different compute option. Maybe I also want to test it locally. Maybe I want to share my agent. I'm building my agent on Lambda, but I want to share my code base with another team that are actually using EKS, right? So I want to make sure my agents are portable. Now, depending on the compute service you choose, you can have different interfaces for exposing your agent functionality. To keep your agent portable and generally best practice, we highly recommend you separate your agent logic from the incoming request interface. So for example, this will allow you to use your agent with API gateway and Lambda functions, right? Business logic is separate from the interface, as well as ALB and ECS and EKS, as well as the newly announced agent core, right? As well as, furthermore, if you keep your logic decoupled from the interface, you can easily test it locally as well, right? So I'll show you how to achieve that as well. So, one recommendation, keep your agent logic, agentic business logic, separated from the interface. It will help you to make your agentic applications more portable. Just to show an example of what it might look like, right? On the right side, this is the business logic of my agentic application, right? It expects user ID and user prompt as parameters, and it doesn't make any assumptions whatsoever about where those parameters are obtained from, right? So you can have a Lambda function extracting these parameters from event payload, or an HTTP application extracting this parameter from HTTP request. It doesn't change the business logic of your agent, making it easier to port across various compute options. So let's see what our architecture looks like so far. We got users on one side and agent on another side. I'll be using Lambda because it's a simple way to run my Python applications with Strands SDK. What's the most common way to expose functionality from Lambda functions? That's right, we'll use API gateway, right? And it will enable users and applications to access agent using plain HTTPS requests. Next, we already discussed that we'll be using Bedrock provided LLMs, and we'll also be using S3 to persist user sessions. So conversation history will be persisted for each user separately. We also discussed that we want authentication and authorization in our agentic solution, right? So we'll use Cognito as identity provider, and we'll use Lambda authorizer to validate JWTs before access is granted. So far, looks pretty solid, right? It's scalable, it's stateless, it includes authentication and authorization. But I think we forgot a few important aspects of running cloud applications, right? We talked about architecture and code, the fun stuff. But what about less fun things like observability, security, governance, CI/CD, and so on? Well, the good news is everything you know about building applications and APIs on AWS is still applicable. Your agent, again, it's just a Python application running on ECS, Lambda, whatever, wherever you want to run your application. So if you look at the architecture, there are so many other AWS components that are natively integrated with the setup. Access across services still protected by IAM. You can use your custom certificate stored in Certificate Manager. Encrypt data using KMS. Use observability services like CloudWatch and X-Ray, security services like GuardDuty, Inspector, and so on and so forth, right? So to give you just as an example, right, here's my agent's observability using CloudWatch metrics and Lambda insights. I don't need to do anything extra to enable this, right? It's just there out of the box because you're using Lambda to run your agent. And as you can see logs at the bottom, right? I'm getting all of that natively just because I'm running on AWS. And it's not just Lambda, it's other compute services as well. So moreover, if you're using OTel compliant observability tooling, Strands SDK natively supports emitting OTel formatted metrics, traces, and logs. So you can monitor how many tokens your prompts consumed, right? What's the end-to-end latency of your LLM? You can trace event loop interactions and so much more. And this is what authorization might look like. My agent, travel agent, knows how to detect that user is not authorized and return an error asking user to properly authenticate. Okay. All right. So far we've built a lot of cool functionality, deployed it to AWS. Let's see if we can actually use it. So I'm going to ask my agent, because it's a travel agent, right? to book me a trip to Paris. The thing is, we've implemented the agent, right? The agentic loop, the persistence, etc. But we still have not equipped this agent with tools, right? We're doing state management, authorization, history, but the agent cannot actually book travel yet. So in order for your agent to interact with external systems or actually being able to take actions, we need to start creating tools. Let's take a look at a simple example to start with, right? I would love my travel agent to detect my current city. So I will need to tell it every time. Unfortunately, at this point, there is no tool for that, right? Yet. So let's implement a tool that will help my agent to detect which city I'm currently based in. So with Strands, you can implement tools right there in the agent code, right? So here you can see a simple Python function that accepts IP address and uses a third-party API to return user's location information formatted as city, region, country, right? Again, making a request to external API and then returns city, region, country. Looks pretty simple. In order for my agent to be able to use this function as a tool, I need to do one simple thing. I need to add the add tool annotation with tool name and description. These parameters are crucial, right? Remember, this is how LLM would know why, when, and how to use your tool. This is the text that will be augmented into the composite prompt that your agent sends to the LLM, right? This is how LLM knows what this tool is for, how to use it, when to use it. So now when I'm creating my agent, I will add my newly created tool to the tools array parameter, as you can see there at the bottom, right? So tools array get user location. And I will add the IP address that the current request is coming from, right? Because the tool requires IP address, right? Where I'm getting IP address, it's HTTP request. I got client IP on that request. So once you see the result, and here you go. Now my agent can detect my location, and you can see it's in the exact format that my tool returned, right? City, region, and country, right? The great thing about Strands SDK is the fact that it comes with a huge collection of tools. You can import and use them out of the box, right? So you can see some of them here on your screens. It's quite versatile, right? So you don't need to implement those tools, right? They're available with Strands. You can just use them in your agents. Now, if built-in tools are not enough, you can obviously, like you saw, build your own custom tools. You can create internal tools, which are implemented as part of the Agentic application package, right? They run within the same process, right? It's essentially the tool that you bundle within the agent package itself. Or you can also use external tools, which are consumed using MCP, the Model Context Protocol. And in this scenario, you would need to configure your agent with the URL of the MCP server, as you can see here on the right side. Okay. So this session is focused on building agents, right? So we will only take a very quick glance at implementing MCP server. We do plan to have a separate webinar talking in depth about actually building MCP. So keep an eye for our upcoming enablements. We'll share the link in chat towards the end of the session. Okay, but for now, we will talk about MCP, but do not expect a major deep dive, right? We just want to understand in a nutshell how to build it. Without going too deep into specifics, let's define what MCP is, right? So like you've seen, agents need tools to perform actions. MCP is a protocol, just like REST or GraphQL, right? It's a protocol that is based on top of HTTP, right? Well, if you use remote MCP servers, and that protocol standardizes how agents talk to tools, right? In our specific scenario, we'll assume a remote MCP server running on AWS. Again, we'll implement it using Lambda for simplicity. And again, right, keep in mind, MCP server is just another microservice. It can also be a piece of Python or TypeScript or whatever code, right, that you run on AWS. You already know how to run microservices. So, you already have a huge leap towards running your MCP servers. Let's actually start with authentication and authorization segment, right? So we already implemented this for our agent, right? You know that user authenticates and user is allowed to communicate with the agent, right? Now we're adding a new component, MCP server. Obviously, travel agent is allowed to talk to MCP server. Again, replace agent and MCP with microservice, and it's exactly the same thing. So travel agent is allowed to talk to that MCP server. However, we do not want user to be allowed to talk directly to that MCP server. That's gonna break our kind of audit chain, right? That brings a lot of undefined behaviors. So we do not want this to happen, right? What it actually means is do not just reuse the JOT token you got from the user to communicate to MCP server, right? Have a different token with different authorization specifics, right? And embed user's identity, right, as either part of that token or maybe some custom HTTP header, right? But the idea is do not reuse the token that you got from user for downstream dependency. Make sure that you're decoupling authorization for different segments, right? You do not want user to suddenly being able to invoke directly your MCP server, right? You haven't planned for this scenario, so do not overcomplicate your setup. Yeah, and now my MCP server is also identity aware, right? It will validate that the request is coming from travel agent, and it will have information about who that user is that is currently, travel agents is currently processing. So I'm going to show you a couple of examples of what MCP tool is going to look like. Again, not going too deep into how to build MCPs. This is one super sophisticated tool called Get Travel Policies, right? It will essentially return travel policies for that particular user. So the tool name and tool description are critical. Again, this is how LLM knows when to invoke your tool, okay? The description is crucial. And then you can see that I'm returning, again, simple example, a list of hard-coded policies. But there's one important thing here, right? It's user aware, right? So I'm extracting in my tool, I'm extracting the information about username in this scenario, and now I can actually adjust the response based on that user information, based on that user context. So for example, maybe some executive is allowed to book luxury cars, right? Because like CEO, right? Maybe they're allowed to book helicopters, I don't know, right? So you can adjust the tool behavior based on user identity, right? This is what this user awareness gives you, right? Let's take another example. Again, this is a dummy tool that will help to book hotels. We're building travel agent, right? I'm defining arguments for that tool, and arguments are crucial. Again, the information about those arguments will go to LLM. So whenever LLM asks agent to use the tool, it will supply this information: city, date, number of nights, etc. And inside of your tool, you can do whatever you want, right? You implement the business logic. And again, the parameters as well as user's identity context is available to you in your tool, okay? So we've created an agent. We've created an MCP server, okay? And the last thing that we need to do is to connect them. Okay? That's essentially the last piece. Now, I promise those are the two last slides with code, right? Essentially, this is how you achieve this, right? So you can see that I'm instantiating MCP client here, and the MCP endpoint will always be the same, but the header, the authorization header, will be different, right? I'm setting the authorization header for my MCP server, and that authorization header is user specific. Again, it can be user-specific token bearer header. It can be generic token, but there is additional header with user's information, right? The thing is, do not reuse token that you got from user, right? The last thing is whenever I'm creating my agent, you can see that at the bottom, the list of tools that it has available will include internal tools. For example, how do I resolve my IP address to my location, right? and external tools, MCP tools. So from LLM's perspective, LLM doesn't know whether it's internal or external. It doesn't really care, right? But my agent has a collection of both internal and external tools. All right, we've been talking for about 45 minutes, right? I think it's time to see the end-to-end demo, right? To emphasize, you will get links to this demo, to these slides, everything, right? So let's see what the experience might look like. Okay, so this is my Cognito login screen, and I'm going to log in with my username Alice and some password. Okay, so I'm logged in, and you can see I'm interfacing with my travel agent, right? So it recognized me, hi Alice, and I'm gonna ask it to book me a party in Paris. You can probably see how many problems we got here, right? So I apologize, Alice, there are issues with your travel request. We only support business travel. We only restrict travel within the United States, right? Okay, let's try something else. Book me a business trip to New York. Just a quick note about our car rental option, because remember, right, we're not allowing luxury. We have sedan and SUV options. Remember, our policy restricts luxury car rentals, right? Okay, and can you provide missing details? Okay, let's see if I can cheat the system. It starts next Monday, lasts for 3 days, rent me a Mercedes. Let's see what happens. Can I hack it? Well, here's a summary of your booking. You got Toyota Corolla in New York. You got your hotel and dates. I booked a standard sedan instead of luxury Mercedes to comply with our corporate travel policy. Would you like to confirm? I'm saying yes, and my trip is confirmed, right? So this is what you can achieve with Agentic system. You're having a conversation. That system is aware of various pieces of information within your organization, like travel policies. That system interacts with different, tools and services, like, booking a travel or, various agentic systems can do different things, right? It can look into a database, it can read from a local file system. Essentially, it's up to you to implement that logic. So, all right, we've been talking about this for 15 minutes, and I see there are a lot of questions, and thanks, Rohan, for answering, for taking the questions in the chat. All right, let's start with summarizing what we've discussed today. You've seen how to build an agentic solution on AWS using Strands SDK, MCP Server, and collection of AWS services. I hope now you also have a better picture in your head regarding what is that mysterious agentic AI system is, right? Again, it's a microservices that implement agentic logic. Agentic systems, they either break the complex task into smaller ones or ask LLM to apply chain of thoughts to break down those tasks, right? They plan out the sequence of actions with the help of LLM. They might use relevant context information along with the plan. They might ask you for missing information if LLM deems that that information is not available yet, but it's required for calling the tool. They will leverage tool calling for executing tasks by invoking APIs or database calls. They bring awareness to the past interactions by adding all the relevant state information to the LLM calls, right? So with help of all of these things like state information, tool responses, intelligence of LLM, they make decisions and execute actions, and they adjust at every step. The core scenario we explored today was this, right? Direct, synchronous human user interaction with the agent. This is also known as agentic chatbot. Agentic, but still a chat, right? So, but this is obviously not the only thing you can implement, right? You can enhance your agentic applications by integrating them with any other system. So, for example, you can implement a webhook called by some third-party service or application that will invoke your agentic workflow. It doesn't have to be a human interaction. Or you can have your agentic workflow to be triggered periodically using Event Bridge Scheduler, or by any custom event coming from Event Bridge. Again, you're just triggering a microservice that implements agentic logic. Or you know what? You're obviously not limited to Event Bridge. You can have your agentic workflow triggered as part of any event. Document uploaded to S3, message published to Kafka or SQS or Kinesis, right? Anything. This gives you a lot of flexibility when you're building those agentic systems. So some final thoughts, right? First, your existing knowledge is your accelerator, right? Yes, you need to understand what agentic system is, right? But keep in mind, we're talking about applications calling LLMs in loops, and you already know how to build applications on AWS. Two, great context leads to great answers. Generic prompts will give you very generic and often quite irrelevant answers, right? Use system prompt, conversation history, tool responses to enrich the context you send to LLM. Better prompts lead to better answers. Important point, better doesn't mean larger, right? All of those prompts are essentially tokens that you're paying for. So better does not equate, larger, right? You need to balance. And the third one is, while your inner engineer might be excited about building a low-level implementation of agentic loop, something that we started with about 40 minutes ago, I would highly encourage you to keep it simple and use battle-tested frameworks and services that allow you to focus on delivering business value. Do not spend time on commodities, right? Differentiate instead, right? Make sure you implement the business workflow. Now, as promised, we're going to be sharing a collection of links that contains everything you've seen today, right? Including docs, slides, the full end-to-end travel agent implementation on GitHub, right? You'll get all of this. We'll send out a follow-up email either later today or tomorrow. You will get everything that you've seen, okay? And please do subscribe to our series because we'll be expanding a lot on building agents, building MCP servers on AWS. Okay, so we're 5 minutes over time. Again, thank you so much for joining today. I hope this session was helpful. Please do register for the series of events that we're running, where I will continue to get those enablements out there. We want to make sure that you're building efficient agentic and GenAI applications on AWS using the services that best fit your use case. With that, thank you so much.